Welcome. In Chapter 17, we will be discussing food, molecular gastronomy, or the chemistry of nutrition. All foods are chemicals. They include three major categories of chemicals: carbohydrates, fats, and proteins. There are also four other smaller categories that are extremely important for nutrition, which are water, vitamins, minerals, and fiber. Throughout this chapter, we will go through all of these major categories of food and describe some of the structural information behind the categories as well as the chemistry that's involved with these food groups. The first group that we'll discuss are the carbohydrates. Carbohydrates include sugars and pasta, rice, fruit. The monosaccharide class, mono stands for one, are our simple sugars. These are going to include regular pure cane sugar, corn syrup, as well as the sugars that can be found inside fruits. Disaccharides are two sugar units. These include sucrose. The monosaccharides are very small, which allows them to be directly absorbed into the bloodstream. These are sugars like glucose and fructose, and also the sugars that you might get from a candy bar or fruit. Sucrose is hydrolyzed into glucose and fructose. So our disaccharides are hydrolyzed, which means that the bond between these is broken and water is added across this bond. Here is a chemical equation to show this. The sucrose reacts with one molecule of water to form glucose and fructose. Generally, an enzyme is used for a hydrolyzation reaction. This is a common theme that we'll see throughout this chapter, where within our body, when a chemical reaction occurs, water is used, as well as an enzyme, which is a large protein that can help make the reaction occur easier and faster. Lactose, which is found in milk, is hydrolyzed in a reaction to form glucose and galactose. This reaction is shown where the lactose reacts with water, and as a disaccharide, it can be broken into its two monosaccharides. Have you guys ever met someone who's lactose intolerant? This occurs when people lack the enzyme necessary for this reaction. The syndrome is called lactose intolerance, and it occurs when somebody does not have the lactase enzyme, which is used to hydrolyze lactose. If you've ever met somebody who has lactose intolerance and they've taken a pill or a powder when they went to eat pizza, this is a replacement for the lactase enzyme. They can supplement their lactase enzyme and then consume lactose. Galactose is converted to glucose during metabolism, and in some cases babies can lack the enzyme that's necessary for this conversion. A synthetic formula can be used to overcome this difficulty. Up until this point, we've talked about the simple carbohydrates. These monosaccharides and disaccharides can easily enter the bloodstream, and then the chemical bonds within the molecules can be broken apart and used for energy. Complex carbohydrates are many monosaccharides or disaccharides linked together into a huge chain. These are called polymers, and they're connected by different linkages. The two main types of linkages are alpha linkages and beta linkages. The starch that we eat in the form of rice or pasta or bread contains mostly alpha linkages, and animals and humans possess the enzymes necessary to hydrolyze these bonds so that the complex carbohydrates can be broken down into glucose, which is a source of energy. Carbohydrates, such as starch, can produce up to 4 kilocalories of energy per gram. Some complex carbohydrates are connected with beta linkages. These are called cellulose. Most humans and animals lack the enzyme necessary to hydrolyze cellulose, but there are some animals that can break these bonds. For those that can't, these serve as a source of fiber or roughage. Animals like rabbits do have the enzymes necessary to break down the beta linkages and consume food that humans can't consume, like hay. Once the complex carbohydrates are broken down into individual glucose molecules, our body can use them as energy. In some cases, we might consume too much sugar or too many carbohydrates. If this occurs, then our body can build these individual sugar molecules back into a branched polymer, and this is going to be called glycogen. This is how we store the excess carbohydrates that our body consumes. And the glycogen is stored as fat. That's the first major food group, carbohydrates. The next group of food we will talk about are fats. Fats are combined from the esters of fatty acids and glycerol. We can metabolize fat for energy, and it produces up to 9 kilocalories of energy per gram. It's also used in producing the structure within our cell membranes. Fats are digested in the small intestine, and we use an enzyme called a lipase to hydrolyze the triacylglycerols into mono and diacylglycerols. On the next slide, we'll go through a figure that explains this. But these lipases simply break the bonds between the fatty acids and the glycerol backbone. The fats can then be stored in fat deposits within the adipose tissue. Let's take a look at the structure of a fat. I'll bring your attention first to the structure in the bottom right corner. This is the glycerol backbone. The glycerol backbone contains 3 hydroxyl groups. Each of these hydroxyl groups has the ability to bind to one of the fatty acids. I like to think of it like a key ring next to your door. The key ring will have a spot to place 3 keys. Each of those keys in this analogy is a fatty acid, and the glycerol backbone is the key ring. Let's take a look at this figure in the bottom left. This is the fat with the fatty acids attached to the glycerol backbone. We can look on the right side of the molecule and see the glycerol backbone. We see the oxygen attached to the 3 carbons. Each of these oxygens is then linked to a fatty acid. Water and lipase can break these bonds and liberate the fatty acids and the glycerol. High consumption of dietary fats and cholesterol have been linked and implicated in cardiovascular disease. This is because the fats can form on the inner wall of arteries a substance called plaque. The plaque will prevent the blood from flowing through the artery. Plaques that clog the arteries contain large amounts of cholesterol. Cholesterol is fat-like steroid that is commonly found in animal tissue, and it's carried throughout the blood by lipoproteins. There are 3 types of lipoproteins: very low density, and high density lipoproteins. We'll focus on the low density and high density. These are considered to be the good and the bad cholesterol. The low density lipoproteins are considered to be bad cholesterol because they carry the cholesterol from the liver to the blood, and these are responsible for the formation of the plaques. The HDLs, or the high density lipoproteins, are considered to be the good cholesterol because they carry the cholesterol from the blood to the liver and help to reduce the amount of plaque that forms in the blood. Roughly 50% of the lipoproteins are HDLs, and roughly 25% are the LDLs. When this percentage or concentration of these 2 proteins becomes skewed, that's when issues can arise with the buildup of plaque. Diets that are high in saturated and trans fats have been linked to high levels of LDL in the blood. Trans fats are formed when unsaturated fats are hydrogenated in order to make margarines or more solid fats. Trans fats are also present in processed foods quite often. We can take a look at the structure to differentiate between saturated and unsaturated fats and cis versus trans fats. In figure A, we have a saturated fat. If we look at the gray atoms, these are the carbon atoms. Between every carbon atom, there is a single bond. This means that those carbons are saturated with hydrogens. Hydrogens are the balls in white. In B and C, we can see that one of the carbons has a double bond. These carbons are bonded by two bonds. This makes them unsaturated fats. The configuration on either side of the double bond differentiates between trans and cis fats. We can see in the trans fat that this carbon and this carbon are on opposite sides of the double bond, where in the cis configuration, the two carbons are on the same side of the double bond. The final major food group that we'll discuss is the protein food group. Proteins are digested into individual amino acids. Let's start from the beginning. We discussed how an atom is composed of neutrons, electrons, and protons. And we also discussed that we could take several atoms and combine them together to form molecules or compounds. Molecules are compounds that have the structure of amino acids are classified as such. There are more than 20 amino acids that are common in our biology and our diet. The body can synthesize a majority of the amino acids, but 9 of the amino acids we must get from other sources. These amino acids are called essential amino acids, and they include isoleucine, lysine, phenylalanine, tryptophan, leucine, methionine, threonine, and valine. The amino acids we can think of as the building blocks for proteins. Amino acids themselves have somewhere between 20 and 50 atoms in them. We can then take between 20 and 1,000 amino acids and combine them together to create proteins. Proteins within our diet can be broken down in order to metabolize and use the amino acids that are present. Complete proteins contain all of the essential amino acids needed for growth. There are several common food groups like lean meat, milk, fish, and eggs, which contain complete proteins. Our body needs these proteins to function, and it requires a rate of about 0.8 grams of protein per kilogram of body weight per day. Without this intake of proteins, a deficiency can occur, which can lead to negative growth and development, as well as discoloration of the skin or hair and a swollen abdomen.